Hello, everyone. Today we are going to discuss a very important topic in the field of biomedicine and drug development, liposome systems. First, let's take a look at the basic situation of liposomes. The content we are going to introduce mainly includes the following three aspects: background introduction of liposomes, description of liposome characteristics, and the main applications of liposomes. The development of liposomes is a history of continuous exploration and innovation. Starting from the conventional liposomes in the 1960s, scientists have conducted in-depth research on them. As time went by, polymer-stabilized liposomes appeared in the 1980s, and there were new developments in the 1990s. Until today, in the 21st century, we have seen a variety of advanced liposome types, such as synthetic lipid liposomes. These developments reflect our deepening understanding of the structure and function of liposomes, as well as the continuous advancement of technical means. Here, I would like to first introduce a common preparation method for liposomes: thin-layer chromatography hydration method. This process is like a carefully choreographed chemical dance. First, we dissolve the lipids in an organic solvent, which is like building a stage for the liposomes. Then, through the clever step of rotary evaporation, the organic solvent is completely evaporated, leaving behind a dry lipid film, which is like building the frame of the stage. Next, adding an aqueous medium to this dry lipid film is like injecting vitality into the stage, and the lipid film begins to swell. Finally, after hydration and stirring, the suspension is extruded through a polycarbonate filter with a specific pore size, so that we get the unilamellar liposomes we need, which are the final performers of this chemical dance. On the basis of basic liposomes, liposomes with different characteristics are obtained through surface modification, each of which has its own unique characteristics and application scenarios. For example, traditional liposomes are the basis of liposome research, which provides an important reference for our subsequent research. P-gylated liposomes give liposomes some special properties by adding polyethylene glycol to the surface of liposomes. It can reduce the chance of liposomes being recognized and cleared by the immune system in the body, just like putting on an invisible cloak for the liposomes, allowing them to circulate in the body for a longer time, thereby increasing the half-life of the drug and enhancing the therapeutic effect of the drug. Responsive liposomes can respond accordingly to the stimulation of the external environment. For example, when encountering specific pH values, temperatures, enzymes, and other stimuli, the structure of the liposomes will change, thereby achieving precise release of the drug. This is like an intelligent drug courier that can accurately deliver the drug at the right place and time. Ligand-targeted liposomes are connected to specific ligand molecules on the surface of liposomes. These ligands can recognize and bind to receptors on the cell surface, so that the liposomes can specifically deliver drugs to target cells. This is like equipping liposomes with a precise navigation system to ensure that drugs can accurately reach diseased cells, improving the pertinence and effectiveness of treatment. The composition of liposomes is very similar to the cell membrane bionic system. The most obvious difference is that the phospholipid molecular layer of liposomes does not have specific membrane protein molecules inside. We have learned that there are many types of liposomes. In addition to the types mentioned above, there are also stealth liposomes, which are better able to evade recognition by the body's immune system. Drug-loaded liposomes, as the name suggests, its main function is to load drugs. Targeted liposomes, emphasizing its ability to accurately deliver drugs to specific cells or tissues. In addition, there are some related nanostructures, such as solid lipid nanoparticles and lipid nanoparticles carrying mRNA. These different types of liposomes and related nanostructures provide us with a wealth of choices in drug development and treatment. We can choose the most suitable liposome system according to different disease types and treatment needs. Next, Let's take a closer look at the structure of liposomes. Liposomes are made up of phospholipid molecules, which have unique structural characteristics. It consists of a polar head and a non-polar tail, like a little tail molecule with a hydrophilic head and a hydrophobic tail. These phospholipid molecules will automatically arrange themselves in an aqueous solution to form a double-layer structure, just like two layers of little tails facing each other, forming the basic framework of liposomes. In this structure, molecules also have a variety of movement modes, such as lateral diffusion, which is like molecules moving left and right on their own floors, and flipping motion, which is like molecules flipping from one layer to another. These movement modes have an important impact on the function and properties of liposomes. For example, lateral diffusion can affect the fluidity and stability of liposomes, while flipping motion may be related to processes such as material exchange and drug release of liposomes. Liposomes have some very important properties that give them great advantages in the field of drug delivery. In terms of stability, liposomes can provide a relatively stable environment for drugs. Whether it is a hydrophilic or hydrophobic drug, liposomes can wrap them inside, protect them from the influence of the external environment, and reduce the decomposition and inactivation of the drug. This is like creating a solid, protective shell for the drug to ensure that the drug can maintain its activity and effectiveness before reaching the target site. Biocompatibility is another important property of liposomes. Liposomes themselves are composed of phospholipid components similar to biological cell membranes, which makes it compatible with the environment in the body after entering the human body and will not cause strong immune responses or other adverse reactions. It is like a friendly visitor that can exist harmoniously in the human body, creating good conditions for drug delivery. Targeting is one of the most prominent characteristics of liposomes. By modifying the surface of liposomes, we can enable them to specifically recognize and bind to target cells or tissues. For example, by connecting specific antibodies, ligands, or other targeting molecules, liposomes can deliver drugs to the lesion site as accurately as a missile, improving the therapeutic effect of the drug while reducing damage to normal tissues. The realization of this targeting makes personalized medicine and precision treatment possible and is an important direction for the development of modern medicine. Liposomes are widely used in drug delivery. Drug loading strategy is one of the key links in the application of liposomes. Different loading strategies can be used for hydrophilic and hydrophobic drugs. For example, for hydrophilic drugs, we can use the aqueous core of liposomes to load drugs. For hydrophobic drugs, they can be encapsulated in the lipid bilayer of liposomes. This ensures that drugs of different properties can be effectively loaded by liposomes, laying the foundation for subsequent drug delivery. The mode of action is also an important aspect of liposome drug delivery. One of the common modes of action is endocytosis. When liposomes enter the body, they can be taken up by cells through endocytosis. In this process, pegylated liposomes can improve the therapeutic effect of drugs by extending the half-life of drugs. In addition, liposomes can also release drugs into the cytoplasm of cells through the endosomal/lysosomal escape mechanism to achieve the effective effect of drugs. Another mode of action is membrane fusion. By connecting a cleavable linker to the surface of the liposome, the linker can be broken when the liposome contacts the cell membrane, thereby achieving fusion of the liposome and the cell membrane and releasing the drug directly into the cytoplasm. This direct cytoplasmic release method can improve the efficiency of the drug and reduce the loss that may occur during the transport of the drug within the cell. Increasing specificity through targeting ligands is another important advantage of liposome drug delivery. We can connect specific targeting ligands, such as antibodies, carbohydrates, etc., to the surface of liposomes. These targeting ligands can recognize and bind to receptors on the surface of target cells, so that the liposomes. In addition to drug delivery, liposomes also play an important role in siRNA delivery. siRNA is a small molecule RNA that plays an important role in gene expression regulation. As a nanoparticle delivery system, liposomes can effectively deliver siRNA into cells. When liposomes carry siRNA into cells, siRNA binds to the RNA-induced silencing complex, RISC, in the cells. The bound siRNA guides RISC to recognize and cut complementary mRNA, resulting in the degradation of mRNA and ultimately achieving regulation of gene expression. This siRNA delivery system provides a new tool and method for gene therapy and disease research, which helps us better understand the mechanism of disease occurrence and explore new treatment strategies. Liposomes also have surprising applications in the field of cosmetics. As people pay more and more attention to skin health and beauty, the research and development of cosmetics has also paid more and more attention to its functionality and safety. The application of liposomes in cosmetic delivery is mainly reflected in its protective effect on the skin. For example, liposomes can be used to protect the skin from damage caused by ultraviolet rays, UVA, UVB, UVC. It can wrap ingredients with sunscreen function inside and then form a protective film on the surface of the skin. When ultraviolet rays irradiate the skin, the sunscreen ingredients in the liposomes can effectively absorb or reflect ultraviolet rays, thereby reducing the damage of ultraviolet rays to the skin. In addition, liposomes can also be used to deliver other ingredients with skincare functions, such as moisturizers, antioxidants, etc., to provide all-round protection and care for the skin. In summary, as an advanced drug delivery and biomedical tool, liposome system has rich types, unique structural characteristics, and many important properties, and has broad application prospects in many fields, such as drug delivery, siRNA delivery, and cosmetic delivery. We believe that with the continuous development of science and technology and the deepening of research, liposome system will play a more important role in the future medical and beauty field.